So I've been getting a number of requests to discuss something that we call countercurrent flow. And to discuss that, first I need to discuss concurrent flow and what that means. So here I've got my little dots. This is some sort of medium, and it is decreasing as it's moving throughout the system because cells are starting to suck it up. So here I've got 16 of these little buggers, here I've got 12, and here I've got 8. Okay, if the blood is moving in the same direction, and we're going to say that it moves slow enough that that it can reach equilibrium. At this point here, this first point, 8 of these guys are going to go into our blood to try to create that equilibrium. By the time we get to this point here, reaching equilibrium would be 6. We already have 8, so we're saturated. We're not going to get any more for that. In reality, what's going to happen is that we're not going to have enough time for all of that stuff to reach equilibrium. So instead what's going to happen is maybe 4 of these guys will be able to make it over here. Okay. When we reach this point here, half of 12 is 6. What that means is that to reach equilibrium, now we can only really grab 2 more and get to 6. All right, because this 4 is going through the blood. So by the time we reach this area here that has 8, half of 8 is 4, this means that we are already saturated. We can't accept any more. And so that creates a limitation. Now, let's reverse the flow and see what happens. To sort of do a side-by-side comparison, I'm going to draw the countercurrent below this. In a countercurrent scenario, we're going to move in the opposite direction of our medium. All right, whoop. So now the vessel's going this way. So it's basically going towards the increasing concentration of whatever molecule it happens to be. So then to reach equilibrium here, it gets 4 of these guys. And then when it heads to the 12, it can grab 2 more and reach equilibrium at 6. Now, when it reaches this area over here, we've got 16, which means that what we can do is we can actually reach equilibrium at up to 8. So now we get 2 more, that gives us 8. What this means is that we actually saturate at a higher level than we did before. What I really want you to focus in on is the fact that here I was able to get up to 8, and here I can only get up to 6 before I saturate. And this is actually with a really small gradient. So this is where that countercurrent is much more efficient at getting in the case of oxygen, blood to a source of saturation. It also can be used for heat exchange, where you're, instead of moving molecules into the bloodstream, you're moving basically hot air. We saw this too in the kidney, and in the kidney it comes into place with the loop of Henle. All right, now if I can add one more, I'll add cross-current flow. And this one's a little bit complicated, but I'm hoping that I can simplify it. So again, I'm going to create my little gradient here. All right, I've got my gradient, and now what happens with our bloodstream is that we basically have one vessel down here, and that vessel is going to split into 3 vessels. All right, so it's going to split into 3 vessels. 1, 2, and they're going to join, and then 3. Kind of amoeba-esque almost. Okay, so what's going to happen? What's going to happen is that this vessel right here is going to try to equilibrate with this guy. So maybe it gets 8 oxygens in it. Then this vessel, which runs through this guy here, is going to try to, try to equilibrate, which gives it 6 because we had 12 in that one. And this one here gets 4 to reach its equilibrium. So the most saturated you can get is a mix of that 8 plus 6 plus 4. If we add all that together and then divide it, it's going to be 18 over 3. The most saturated that you can get here is 6. And remember, with countercurrent, we actually got up to 8. The reason is because you're having to reach equilibrium. Now, in this case, if the medium, which these green dots, are moving really fast, what that means is that now we always have a fresh source coming in, and that would actually make the level here and here effectively a little bit higher, and it would allow us a lot more, a higher level of saturation, because basically we'd have so much fresh medium coming in, we wouldn't be able to suck the nutrient or oxygen out of it fast enough. So remember with this that flow is actually really important, because if the flow is really fast, you're always getting a fresh supply, you're not depleting it at all. In this case that I've drawn here, you're actually depleting it, which would be like a slow flow case.